In these slides, we'll start talking about model-based collaborative filtering approach. The most basic of them is matrix factorization. Remember the classification of collaborative filtering into memory-based and model-based methods. The distinguishing aspect is that in the latter, we built a machine learning model that describes the observed user item feedback and can then predict user item interactions. We will focus on matrix factorization, which is the most important model-based approach. We will motivate it and discuss singular value decomposition and how it is related to matrix factorization. Then we will present a concrete implementation of basic matrix factorization before adding more complexity to it. We will also say a few things about the Netflix prize competition. Other model-based approaches will be covered later. Let's first motivate matrix factorization. In general, the ratings matrix contains all the information about user preferences over items. However, we can say that this is a very detailed representation and perhaps unnecessarily so. We can make the assumption that user preferences are not overly complex. That is, to explain my movie preferences, I don't really need to list all the movies that I like. These preferences can be described more compactly. For example, I can say that I like Steven Spielberg as a director, sci-fi movies, and Harrison Ford as an actor. Given this assumption, the goal is to find a representation of user preferences that is compact and largely explains the observed user behavior, that is, the observed ratings. The benefits of a more compact representation should be obvious in terms of efficiency. Compactness means faster recommendations, particularly compared to the memory-based collaborative filtering approaches. But also, in terms of effectiveness, we can expect a compact representation to only capture what is useful, the signal, and remove what is redundant, the noise. It would focus on the general trends that capture user preferences. Luckily, we know of techniques that can achieve these goals. There is a popular approach called singular value decomposition, or SVD, that can compress data arranged in a matrix. We thus first overview SVD before adapting it for our case of compressing the ratings matrix. So let's introduce SVD. You can think of SVD as a method to factorize a matrix, but what does that mean? We can factorize a natural number into simpler products, say of primes. For example, 24 equals 2 times 3 times 4. We can also factorize a matrix into a product of more elementary matrices. Here is a concrete definition of SVD. We assume we are given a matrix M of size m by n. Then SVD factorizes it into 3 matrices. In the figure below, the original matrix is shown in blue and is factorized into a product of 3 matrices with special properties. The square U matrix shown in yellow has size m by m and is orthogonal. Similarly, the square V matrix shown in green has size n by n and is also orthogonal. What is left is the gray matrix sigma that has the same shape as the blue matrix but is diagonal. That is, it only has values in its shaded diagonal. All other entries are 0. To be more precise, the non-zero values are called singular, and they are as many as the smallest dimension of the original matrix. It is worth mentioning that the factorization is not unique. That is, there can be different U, V, sigma matrices so that their product equals M. Okay, so we have the mathematical tool to express a matrix as a product of more elementary matrices. Certainly, this is not a more compact representation. But how can we get a more compact representation? Well, this comes from a nice property of SVD. We can create a so-called low-rank matrix approximation. And the way we do that is by keeping the k largest singular values and setting the rest to 0. This implies that we keep only the columns of U and V that correspond to the k largest singular values. In the figure, this means that the dark shaded part of U and V matter. The other parts will be multiplied by a 0 term in the sigma array and thus will not contribute. We denote as M hat the product of these truncated matrices. This is the truncated SVD of the original matrix, and there is a theorem that says that M hat is the best approximation to the original M. Best here means under the total squared error, and approximation means any matrix that has rank k, the number of singular values preserved. So, in practice, we can do the SVD, truncate it, and get a good approximation that we assume is clear of any noise. Let's try to apply this idea to our ratings matrix R. Recall that we have M users, the rows, and N items, the columns. By keeping k singular values, what we get is an approximation R hat. We can think of k as representing the number of features that are necessary to express users' preferences. Recall that we look for a compact representation of user preferences. Each feature captures a dimension of preference. For example, one dimension could be comedy versus drama. Another could be the leading roles being female or male. Matrix sigma conveys the overall significance of the features. For example, the comedy versus drama dimension is the most important in explaining the preferences and so has a high significance and thus a high singular value. It is interesting to see what the truncated matrices U hat and V hat capture. Well, U hat captures the user's interests as expressed in terms of the k features. V hat captures the item's description in terms of the same k features. Let's see how the user's tastes and items' descriptions in terms of the key features interoperate to create the ratings. Consider a specific user item pair u, I. It is highlighted in the blue matrix R hat. The row of the U hat yellow matrix corresponding to user U is also highlighted. Similarly, the row corresponding to item I is highlighted in V. Note that the green matrix is V hat's transpose, and hence a column is highlighted here. The sum over all features of a user feature, an item feature, and the feature significance equal the approximate or predicted rating of a user U to item I. So, to summarize, a target rating can be approximated by using the feature representations of the target user and the target item after scaling them by the feature significance. So it seems we have reached our goal. From the ratings matrix, compute the truncated SVD. But there is an issue. SVD can be defined only when the complete matrix is known. It cannot work assuming missing values. This is in contrast to our case, where we have observed a really sparse ratings matrix and we would like to predict the missing ratings. Okay, so what can we do? An approach explored in the past was to actually fill in the missing ratings, do the SVD, truncate it, and use the truncation to predict the missing ratings. There were different ideas on how to fill in missing ratings. The simplest would be to normalize known ratings, say mean center, and then fill in with zeros. It turns out, however, that there is a better approach that does not need to fill in missing ratings and which gives better results. The idea is to focus on what we want to find out, that is the user and item features, so that they approximate what we know from the ratings matrix. Having seen how truncated SVD works and what is the problem with missing values in the ratings matrix, we now describe matrix factorization. We start by transitioning from SVD to matrix factorization by simplifying a few things. Specifically, we can get rid of the significance diagonal matrix. Its contribution can be included either in the user or the item matrices. This has some implications, namely, it does not retain the orthogonality properties of the matrices, but we do not really care about that. Okay, so now our goal is to simply find a user feature matrix P and an item feature matrix Q. A column matrix PU represents the interests of user U. Similarly, a column vector QU represents the description of item I, both in terms of the K features. Moreover, the inner product of these two vectors gives a predicted rating of user U to item I, to summate the ratings matrix. Thus, our problem is how to construct the yellow and green matrix so that the blue is a good approximation. Before discussing how we can get user and item feature matrices, we discuss what the features might mean. Imagine that we have k features, and these features define a vector space. Each user and each item becomes a point in this space. For example, consider that items are movies and that we have only two features. We don't know what these features represent, but assume for this example that the first feature indicates whether the movie is targeted at male versus female audiences. Similarly, assume that the second feature is whether the movie has a serious theme or has a more escapist theme. The vector space of these two features can be nicely illustrated in two dimensions as shown in the figure, where the former feature is the x-axis and the latter the y-axis. Each movie is a point in the 2D plane. For example, Independence Day is a very escapist movie targeted mainly for male audiences. On the other hand, Sense and Sensibility is geared towards females and has a much more serious plot. Moreover, each user becomes a point in this 2D plane. For example, Gus on the bottom right corner has a clear taste for escapist male-geared movies. Okay, so what does the inner product between a user feature vector and an item feature vector represents? In vector spaces like the one depicted here, the inner product is a measure of distance, or more accurately, similarity. When 2 points have a large inner product, then they must be close to each other. In our feature space, if the user is close to an item, then this means that the predicted rating is high. After motivating matrix factorization, it is now time to discuss how to perform it. We restate the goal. Find a user feature matrix P and an item feature matrix Q so that the rating of some user U to some item I is predicted as the inner product of the feature vectors of U and I. We will treat this problem as a machine learning task. Specifically, matrices P and Q contain the parameters that we need to learn. These parameters should achieve two goals. First goal is that the prediction on known ratings is accurate. Second goal is that the prediction can generalize well to unknown ratings. We can test this by using some test data. Let's study these goals in detail. First up is to make sure predictions for known ratings are accurate. Consider some known rating R of user U to item I. Given matrices P and Q, the predicted rating R hat is given by an inner product. We measure the prediction error as the difference between the actual rating and its prediction. Typically, we want to minimize the square of this error. Using this square means we tolerate small deviations and penalize larger deviations more heavily. We consider the squared errors over all known ratings and compute its mean, called the mean squared error or MSE. In this last formula, R denotes the set of known ratings. Let's move now to the second goal, which is to be able to predict well unknown ratings. This is a hard task in general. The idea is to avoid the problem of overfitting. Overfitting occurs when we learn P and Q matrices that minimize the total error, that is MSE, for the known ratings, but have terrible accuracy for unknown ratings, which is actually what we care for. The figure at the top right succinctly describes the problem with overfitting. Suppose we want to create a model that predicts the price of a house given its size. We know some examples represented as crosses in the price-size plane. The figures show three different models depicted as the blue lines that can be used to predict price given size. The left figure is a very simplistic model that underfits the data, meaning that it has low accuracy for the known examples and low accuracy for the unknown examples. The right figure shows the other extreme where overfitting occurs. If we are given 5 points in the plane, then there exists a polynomial of degree 4 that crosses these 5 points. This model is the blue line shown. As a result, the total error is 0 for the 5 known examples. However, the model looks quite complex and is highly unlikely that it will be a good fit for unknown examples. So, overfitting means high accuracy for known examples, but low accuracy for unknown examples. Ideally, we want to achieve a fit like that in the middle. That blue line is not complicated. It is a second-degree polynomial and approximates the known examples quite well. This line is more likely to also be a good fit for the unknown examples. So, returning to our case, we want to find the just right parameters in P and Q. A standard approach to avoid overfitting is to penalize model complexity. We do this with regularization. Specifically, we require the parameters to have small and rather uniform values. We want to avoid very large parameters that probably imply overfitting. More concretely, we want to minimize the sum of squares of each parameter. The effect or strength of regularization is controlled by a hyperparameter lambda. Hyperparameter means that it is not part of the model and only concerns the learning process. Its ideal value has to be externally determined. So, in addition to minimizing the mean squared error, MSE, achieving thus goal G1, we want to also minimize the regularization term, achieving thus goal G2. Putting the two goals together, we formulate our learning task. Find matrices P and Q such that the following total cost is minimized. This total cost is just the sum of the MSE and the regularization term. There are several ways to solve the above optimization problem. Here we will present the stochastic gradient descent or SGD method. Another popular approach that you may see in the literature is the alternating least squares or ALS method. Briefly, the idea in ALS is to assume one matrix is fixed, say P, and use the closed formula to compute the optimal value of the other matrix Q. Then we alternate, given Q values, find the best P values, and continue like this. Before presenting SGD for matrix factorization, we provide some background in gradient descent. The gradient of a function of many variables, like the total cost is a function of all the parameters, is a vector pointing at the direction that causes the maximum increase in the function. In the case of a function of a single variable, it is the derivative or slope of the function. The figure at the top right shows an example. The blue line is the cost function that has a single variable, the parameter theta. The gradient at a particular point, for example the dark circle, indicates the slope of the function. If we want to minimize the function, we want to go towards the opposite direction indicated by the gradient. That is, we can take a step in that direction, compute the gradient again, and proceed similarly. This is the idea of the gradient descent algorithm. Move downwards towards the gradient direction, which decreases the cost function. We start at an arbitrary random point. This means we initialize randomly all parameters. Then we enter an iterative process which we repeat until we are happy with the cost value we have achieved. At that point we say the values have converged. At each iteration we update each parameter by a small step towards the opposite direction of the partial derivative. The size of the step is controlled by the learning rate eta. So let's now move to describing SGD. One problem with gradient descent is that for each step we need to compute the gradient of the total cost function, meaning that we need to sum over all the training examples. This takes a lot of time. Instead, in each step of SGD, we only compute the gradient of the cost of one training example. To do this, we need to rewrite the total cost function as the average of cost functions for one example. Here, j of I is this single cost function. So, instead of computing the gradient of j, we compute the gradient of ji. The SGD algorithm operates as follows. First, it shuffles the training examples. It also randomly initializes the parameters to be learned. Then it executes a nested loop. The outer main loop is executed until convergence, as in gradient descent. In the inner loop, all training examples are considered. This is called an epoch. The inner loop examines each training example, computes the gradient of the cost function, and updates all parameters. After several epochs, the algorithm terminates and the model parameters are determined. Let's now apply SGD for matrix factorization. The parameters we need to learn are the user and item features. They are contained in the P and Q matrices. We collectively call them theta. How many parameters are there? Well, every user and every item has a feature vector of dimension k, so you can do the math. Okay, so here is our total cost function j of theta. It contains the mean squared error and the regularization term. The error EUI is the difference of the actual from the predicted rating. Remember that to apply SGD, we want to rewrite the total cost as the average cost per rating. We write this as JUI, and it is equal to the formula shown here. The next step is to compute the gradient of the cost function. This consists of the partial derivatives with respect to each parameter. So let's consider a user feature PU. The partial derivative is given by this formula. To verify this, you need to replace EUI with its formula and apply the chain rule. Moreover, you should see that among all parameters in the regularization term, only the term PU squared depends on PU. The partial derivative with respect to an item feature QI can be symmetrically derived. We are now ready to present the SGD algorithm for learning the parameters in matrix factorization. Initially, we randomly shuffle the given ratings and randomly initialize all parameters. Then, the outer loop is repeated until convergence. In each inner loop iteration, a rating UI is examined. The predicted rating is computed by the inner product of PU with QI. The error is then computed. Based on this error, we compute the gradient. We multiply it by the learning rate eta and subtract it from PU and QI. That's it. We have now computed the parameters in P and Q that best fit the given ratings. We have presented the simplest version of matrix factorization. In the next few slides, we will consider slightly more complicated models that seek to increase effectiveness. Let's revisit an idea we discussed in memory-based collaborative filtering. There, instead of predicting ratings, we were predicting rating deviations. In the case of user-to-user, the deviations were from the user's average rating. In the case of item-to-item, the deviations were from the item's average rating. We can think of these average ratings as if they were acting as baseline estimates of any missing rating. Let's apply the same idea to matrix factorization. Actually, we'll slightly generalize the baseline estimates. Now we assume that the baseline rating for user U to item I depends on three terms. Mu is the global average rating in the dataset. This is independent of the target user or item. Then we have the term BU, which is specific for user U and indicates the user's bias in ratings. We also have the symmetric term BI, which is specific for item I and indicates the item's bias in ratings. To understand what these terms mean, let's see an example. What is the rating of Titanic by Joe? Among all ratings, the average rating is 3.7 out of 5 stars. This is mu. Joe specifically is a critical user and tends to rate 0.3 stars lower. This is Joe's personal bias, the term BU. Titanic is considered a good movie and tends to get rated with 0.5 stars above the average movie. This is the term BI. Put all three terms together, we estimate Joe's rating of Titanic to be 3.7 minus 0.3 plus 0.5 equals 3.9. Remember, in memory-based approaches, we were predicting rating deviations from the average rating. Here we will do a similar thing and predict rating deviations from the baseline estimate. This means that the inner product of PU and QI gives us a rating deviation. To compute the predicted rating, we need to add back the baseline estimate for the target user and item. So the predicted rating is now as shown here. There are now additional terms to learn. The bias terms for each user and each item. One question to think about is how many parameters in total this model has. The SCD learning algorithm should randomly initialize these additional parameters and update them with each rating. The update formulas are easy to derive and are shown here. Let's now proceed to include additional sources of data that can be exploited for recommendations. We assume that we know a set of items that the user has interacted with. Can be clicks, likes, purchases, etc. This is implicit feedback in general. Hereafter, we will simply assume this type of feedback to be clicks. Moreover, we assume the binary case where an item was clicked or not. Let N of U denote the set of items the user U has clicked. The intuition with using implicit feedback is that it conveys information about a user preferences. Next, we will present an idea about incorporating this feedback into matrix factorization. For each item, we will introduce an additional vector of features. Let yi denote the vector for item I. This vector is separate from the vector qi. This means we are introducing additional parameters to capture the implicit feedback. Think of the vector yi as describing the item's tendency to receive clicks. The next step is to describe a user based on her or his implicit feedback. We will not use additional user features for that. Instead, the idea is to describe a user based on her or his clicked items. So the user's preferences based on implicit feedback is captured by the sum of the y vectors for each item the user has clicked. Observe that now we have two views to characterize a user based on latent features. First is the direct using the QUser vector. The second is the indirect via the Y item vectors. So now the user model combines these two views. Putting it all together, we obtain this formula for predicting ratings. The yellow part is the baseline estimate that we previously introduced. The green part is the latent feature vectors of the items that we have previously used. The blue part contains the user model and consists of two terms. The P vector, as in standard matrix factorization, and the second term that sums up the latent Y vector. This second term is normalized with the number of items the user has clicked. This is the most complex model that we will see in matrix factorization. In literature, it is often called SVD++ to distinguish it from the basic MF method we first introduced. The SVD++ model shows us that the matrix factorization model is quite flexible in the sense that it can easily integrate additional data sources or signals. One example was to extend the user model by introducing information about implicit feedback. The same idea can be further exploited to incorporate other user attributes such as demographics. So how can we do that? Well, one way is to turn each attribute value into a separate feature and introduce a feature vector for it. For example, for each age group, we can define a binary feature. Is the user in this age group? These feature vectors can be added to the user model, the blue part in the previous slide. The idea of introducing feature vectors for additional sources of information and then including them in the model is the key mechanism behind factorization machines, which we will review later. It should also be noted that nothing stops us from using this very idea to incorporate item content in the model when available. In this case, we will be adding this information in the item model green part of the previous slides. We are now going to talk a bit about the Netflix prize competition that sparked a lot of research around matrix factorization techniques. The competition started on October 2006, and the goal was to devise a method that gives better recommendations than Netflix. The recommendation engine of Netflix was called Cinematch and was based on an item-to-item collaborative filtering approach using the Pearson correlation coefficient to compute item similarities. The objective was to beat Cinemats by reducing the mean squared error, or more precisely its squared root called RMSE, by a factor of 10%. The winner would receive the grand prize of $1 million. This was thought to be a very hard challenge, so to motivate people to keep working on the project, Netflix would award a progress prize of $50,000 at the end of every year to the team or person having the best performance thus far. The competition ended on September 2009 after awarding 2 progress prizes. In terms of the data involved, it contained 100 million ratings from around 480,000 users on 18,000 movies. This data was split into 2 parts. The probe set was the training dataset released. The qualifying dataset contained user-to-item pairs but no ratings. The competition required a participant to predict all these missing ratings. Internally and hidden from the participants, Netflix had a split of the qualifying sets into a quiz and a test subset. The quiz subset was used to record the current ranking of participants. The test set was used for giving out the awards. Let us see the progress of the submissions just before the end of the first year. What you see in this graph is a distribution of submissions with respect to their error improvement. Y-axis is the number of submissions, X-axis is the percent improvement. Near the end of the figure you see the 0% mark. Anything before that are submissions doing worse than Cinemats. Only submissions right of 0% are actually improvements. The red arrows indicate Netflix guesses on what the submissions might be computing. For example, there were a few submissions that were returning 1 for all the missing ratings. It turns out that the fixed rating of 4 is a more accurate ratings predictor compared to 1, 2, 3, 5 with only 20% worse performance. Let us now zoom in on the methods that stand a chance. Here we see the user average being used and the item average being used. Right exactly at the 0% mark is the item-to-item collaborative filtering approach that we know Netflix uses. At around the 4% mark, most of the methods were using SVD-like matrix factorization. There were also a few leaders that were achieving almost 8% improvement. What we saw in the previous zoomed-in figure is that a lot of methods are doing SVD-like stuff. Why is that? Well, very early, just as the competition started, a person named Brandon Webb, with the alias of Simon Funk, started blogging his experiences with playing with a dataset released and applying SVD. It is worth spending a few minutes at his blog. Basically, he was publicly documented and in great detail a very practical way to overcome the difficulties of SVD using a method that is very close to the SGD training of the basic matrix factorization technique we described before. This algorithm came to be known as Funk's SVD and was considered a landmark at that point. So that is why lots of submissions had roughly similar performance at the 4% improvement level. But to go beyond the 4% of basic matrix factorization, some new ideas were necessary. The RMSE of cinemas was 0.9514. So to get the grand prize, you should achieve an RMSE of 0.8563. This figure plots the RMSE of a method with respect to the number of parameters it has. The numbers shown is the latent factor dimensionality. The red line here is the basic matrix factorization. The blue line beneath that was the matrix factorization method with improved baseline estimates that we discussed. Even below that is the SVD++ method that uses information about implicit feedback. To go towards the 8% improvement, the participants had to model temporal effects like the mean rating baselines drifting over time. At the end of the first year, a team won the Progress Prize by reaching almost 8.5% improvement. They later joined forces with another team to achieve a 9.5% improvement. In the end, another team joined and they won the grand prize with a 10.06% improvement. We should note that the winning solution was not a single recommender, rather it was a blend of multiple recommenders. One of the best performing single methods was SVD++. Here are some links for additional reading on the Netflix prize competition if you are interested. Each of the three teams that joined forces in the end documents their own viewpoint.